congestion. So thank you very much.
Okay, thank you. I would like to start by thanking the organizing committee, in particular to Jorge, for inviting me to come here. It's my very first time in Brazil, so in particular in Rio. And for a Portuguese person, actually, I mean, there is this very nice connection. So it has been a pleasure, and I'm really loving the city. So I hope this is the first of many more visits to KAUST. So the work that I'm going to present here is a joint work with Davi Evangelista, which is a PhD student of Diogo, and Levon Nuberken, who is a postdoc in the research group of Diogo, and also Vardan, who until recently was also a postdoc in the research group of Diogo. So this is a KAUST production. And what I'm going to talk about is on first-order stationary mean-field games. So Diogo already did a great introduction and overview on mean-field games. So by now you are quite comfortable with what mean-field games are. But just to recall, at least, just it addresses the study of strategic decision-making in large populations of interacting agents, and these agents are identical, rational, and play non-cooperative differential games. And the work that I'm going to present here, we want to address a phenomenon which is that the agents face a high cost of moving in high-density regions, and Diogo already elaborated a little bit on these problems, and these are called the congestion problems. So in this work that I'm going to present here, the cost is determined by this Lagrangian. Here, in principle, this parameter could be only positive, but here we'll see for reasons why we consider it to be greater or equal than 1. Alpha is less or equal than gamma, and this gamma prime is just the conjugate of gamma. V is our potential. For the moment, let's think of it as a C infinity function, and this G, the coupling, it is given by the derivative of some convex function, and I mean here it is just, namely essentially we are saying that G is increasing, and in this setting, okay. So given the density of the agents M, a typical agent seeks to minimize the long time average cost, which is given by this, and then I'm just plugging in the expression of our Lagrangian, and so this is what a typical agent seeks to minimize, and you see, because of this term here, alpha is the congestion parameter, it makes it more expensive to move in dense areas. And the higher the alpha, the harder it is to move in dense areas. And from the PDE point of view, which the connection here, the derivation Diogo already mentioned a little bit, we are led to this problem. So here we are. So this is our Hamilton-Jacobi equation. Here our Fokker-Planck equation, and we ask for the density to be non-negative, and we are normalizing it. So it is a density of a probability measure, and so this is as before. So I will refer this to as our problem in terms of EDP. I wrote it in Portuguese. PDEs, and here we will be working in, so this is the TD is the D-dimensional torus, so we are working the periodic setting. I mean, not always it is the most natural setting to work in, but it already addresses the main difficulties of this kind of problems, and it facilitates our life because essentially we don't have to work with terms on the boundary. So what else? So and as already Diogo explained, I mean, we have to add this constant in order to ensure existence of solutions, and you can think of it as being the average cost per unit of time associated to our Lagrangian. So so we want to solve this problem, namely we want to find solutions to this problem. And do solutions exist? Are they smooth, and are they classical, and so on and so forth? So talking a little bit about previous works in the literature, I'm not going into detail what each person did, I just want to make some remarks. So here I will just mention some that deal with congestion problems. But the thing that I want to highlight for the first two slides, these works are either in the context of second order problems or time-dependent problems. And regarding stationary first order mean field games, there is not much known apart from some works in the, so this is still, like I was saying, in either second order or time-dependent setting. And apart from these three works, which essentially it is the 1D, so related works and essentially trying to establish some properties in the 1D setting, and this other work that Diogo already mentioned, that where you prove this very weak notion of existence of these weak solutions induced by monotonicity. As you have seen as the definition, it is a weak notion of solutions, and for the congestion case, we were not able so far to improve the result, namely establishing some more properties. So far there is not much known in the context of congestion problems, first order, stationary. Okay. And the difference, for example, with the second order or the time dependent, is that usually one can prove some a priori estimates that bootstrap some kind of regularity and help us proving existence of some kind of solution. Here, in the paper that I'm presenting here, we were also able to establish some a priori estimates, first order and second order estimates. They are interesting, but they are not alone. They are not enough to give us anything regarding existence or of solutions. And also, it turns out that in many situations, we don't really have classical solutions. And let me show you, because it's simple to prove. So, for example, so this is the problem that I am addressing. So, for example, think on the case. So set P equal to 0. I didn't comment on P, that appears, but P, and then when we come to the numerics, I will comment again. P determines a preferred direction of motion. And we'll see in the numerical simulations that I'm going to present in the end. But for the moment, assume that P is equal to 0, gamma is equal to 2, so we are in the quadratic case, and capital G is m squared over 2, which implies that little g is just m. So then what is the system that we get? We get du to 2 over 2m to the alpha plus v of x equals to m plus h bar. And then for the second equation, you get the divergence of m1 minus alpha and then just du, because p is equal to 0 and gamma is equal to 2. Okay. So assume that you have a smooth solution, meaning, of course, you cannot allow m to be 0 because it appears in the denominator. So it's smooth with m greater or equal than 0 and normalized. Okay, so then what can you do? So assume that you would have such a smooth solution. So then what you do? So multiply the second equation by u and integrate. So then if you integrate by parts, okay, we have periodic conditions. So the term on the boundary does not appear. And then we get that m du squared is equal to 0. Okay, but because we are assuming that m is strictly positive, then this means that U is constant. Okay. So, but if U is constant, then we go back to this equation. Okay, we are assuming that we have a smooth solution. This term disappears, so we just get this identity, right? So you get that M is equal to V of x minus H bar. But then, because the integral of M is equal to 1, you actually can compute the value of H bar. And then you conclude that M has to be equal to V of x minus the integral of V plus 1, right? It integrates to 1. So then you look at this and then you see, well, you can come up with infinite V's that are periodic, that for which this is less or, I don't know if I made a, but for which this is less or equal than minus 1, right? And then you get the contradiction, because then it means that M is less or equal than 0, and your assumption was that sorry, I want M strictly positive. I was assuming that I have a smooth solution. So we get the contradiction. So this shows that in general, and in many situations, you cannot expect to have a smooth solution. Okay, so then how can, what was our strategy to solve this problem? And our success in studying this problem was the realization that actually there is a variation principle behind this problem, this system. Namely, we realize that if we have a pair UM, if it is a smooth minimizer for this functional under this constraint, then we can find H bar for which this triplet solves our mean field game. Okay? And so in other words, it is just our mean field game is the Euler-Lagrange of this functional J. So then another way to look at the problem in order to try to find existence and study also the uniqueness of solution, it is to look at the minimization problem associated with this functional J. But of course, as we have seen, we have somehow to address the case in which M can actually vanish on a set of positive measure. And so what do? Well, we extended our functional. So if M is different from 0, then this is just the function that was appearing before. I mean, it is our function. And then, and then you do what is reasonable. If P is equal to minus capital P, and M is equal to 0, well, you set it to be equal to 0. Otherwise, if P is different from minus capital P, then you set it to be plus infinite. And then you end up studying these variational problems. So you look for minimizers for our functional, the functional that I've just shown you, and we look for minimizers in this set. So we are looking for U's that are in a certain W1Q for some Q greater or equal than 0, M in LR, and here we are asking the average of U to be 0 because our problem is determined up to, does not see constants, right? In terms of U, if I go back, I don't go back. I did go back a lot, no, sorry. Right, so if we add a constant to U, our problem doesn't see it, so we are fixing U, and then the restrictions for M. So this is the problem we are addressing, and so allow me, instead of showing you in slides what are the main steps, what are the techniques that we prove, I will do mostly the proof or part of the proof on the board. So what are the key ingredients when we have a minimization problem? What are the key ingredients to prove existence of solutions? Well, we take a minimizing sequence, and then we hope for some compactness, and then we hope also that our functional is lower semi-continuous with respect to the topology that we prove that we have compactness, right? So okay, so let's do this. So let's take a minimizing sequence, so UJs, MJs, and for the moment I will not tell you what Q and what R are. They will naturally, somehow naturally will appear in a QR such that the limit of J bar UJ MJ is equal to the minimum in principle should be infimum, but okay, the minimum actually does exist, so let me write minimum. And I will call this M. Well, of course, extracting a subsequence if necessary, you can assume that this limit is actually a limit and that this is finite. So assume for a moment that you can prove that, so this would be our test number 1, that you can prove that Uj converges to U in some W on Q, that Mj converges to some M in LR, and that your functional is lower semi-continuous. Then what happens? So below you have, so let me call these bars U bar and bar. If your functional J bar is lower semi-continuous, but for sure the infimum is less or equal than this value, because if you prove, of course, if you prove that U bar and bar does belong here. And then you have equalities, and then you prove existence of solution. So this is our task somehow, is to prove establish some kind of compactness, and then prove that the functional is lower semi-continuous. Okay, so then let's take a look at our functional. Maybe what can be nice to appear here is the definition of maybe F. Okay. Okay, so what is the upper bound that we have? Well, if you take, so regarding the minimum, an upper bound that we have for our M, you take as test functions, well, U identically equal to 0, M, and M identically equal to 1. They are good test functions. And then what happens? Well, if you replace, because U is equal to 0, the gradient of U is equal to 0, you replace, so you only get, so for F bar and M is different from 0, so you go to the first expression, and you just get the P over gamma, and then gamma alpha minus 1. And then you can bound from above minus V by the minus the sup. Yes. Sorry, no. I'm taking. So I'm taking M equal to 1, so it is just the integral of V. Fine, it is a constant. plus G of 1. So from above, we are fine. And then from below. Well, from below, you use that. Actually, it's going to be a minimum. So let's look at the functional, and then we would take the infimum of all admissible u's. Well, given any u and any m, for sure, f bar is non-negative. So 0. And then from below, then it is the supremium. You can bound this, the supremium of v on the torus, times the integral of m, but the integral of m is equal to 1. So this is a bound for this term. And then now our g, it's convex, you use Janssen's inequality, so the integral can go inside. So you get g of the integral of m, but the integral of m is 1. So you get from below g of 1. So we have, and then you would take, because this does not depend on u and m, you take the infimum, and you get this bound for the infimum. So you have uniform bounds for the infimum. Fine. So now, how do we extract compactness? So what we prove is that the supremium, so in J, for our minimizing sequence, of J bar of uj mj is less or equal than some constant. Okay, and then we observe in absolute value. And then we observe the following. So I'm going to put here two positive quantities, and then this will give us the compactness. So this is one, f bar is non-negative, and the other one, like I was saying before, it is non-negative by Janssen's inequality. So this is non-negative, this is non-negative. And then how do we bound these things? So essentially, what is the difference from these two terms to our J bar? Well, this is essentially, this is J bar, and then what do we have to compensate? We have to compensate the term in V. So the term is here. So we want to add it so that it disappears in the sum. And then minus G of 1. And then, as we proved, this is bounded by a constant. This is, again, you can take for example, the L infinity norm of V, and then again you get the integral of m, which is equal to 1, and then this is a constant. So this is a constant, so these two quantities are bounded. And now they are non-negative, so each one is bounded. So what does it tell us? The fact that this term, this positive term, is bounded. Well, it tells us that for sure the integrand has to be finite almost everywhere. Well, but if it has to be finite almost everywhere, for sure the gradient of uj, so mj has to be positive whenever the gradient of uj is equal to minus p, our capital P. So mj has to be positive almost everywhere in the set where the gradient of uj is different from minus p. Otherwise, f bar is equal to plus infinity. It cannot be, because we just proved that it cannot be. Okay, and let me give it a name. Let me call it uj. So finally, and also, and of course, this is equal because this set where m is positive, this is just because where the gradient of uj, sorry, when what do I want to say? Okay. Well, because why in uj? Because outside, if we are outside uj, mj has to be equal to 0. So they are both equal to 0, and by definition of f bar, this is equal to 0. So we can integrate. So this integral is equal to the integral in uj, but here this is just the expression of f is given by this, and we know that this is finite. So finally, our compactness. So then we observe the following. The integral in the torus of gradient of uj plus p to the gamma, sorry, this is equal, of course, in uj, because otherwise this is 0, right? Outside uj, this is 0. And then this is the game. So we divide, so we put here our constants if you want. No, we don't need. So mj to the alpha over alpha minus 1, and now I'm doing it wrong. No, I'm doing it right. No, I'm doing it wrong, sorry. Alpha. Let me check, sorry. It was okay. And then you use Young's inequality. Use Young's inequality, and then you use Young's inequality. So this term, you are going to put it to the power of alpha, the other one to the power of alpha over alpha minus 1, and then this is less or equal than 1 over alpha. Sorry, yeah, because here actually what I want is this. Thank you. Okay, this is what I want, in fact. And now, so like I was saying, so this to the 1 to the alpha, and then mj alpha minus 1 plus alpha over alpha minus 1. And then this is m. And now this is equal to 1, right? This is a constant. And this is what we just proved, that it is bounded. Okay? And so what are we concluding? We are concluding because the averages of uj are equal to 0, so you use Poincare-Havitinger inequality, and you prove that the uj's are bounded. So the conclusion, in W1, now gamma over alpha. Okay, and so let me see if this does not lock. Okay. And now, so if, now there are two cases. If alpha is strictly less than gamma, we are fine, right? because we have, it's a reflexive space, so up to a subsequence we can in fact extract a convergent subsequence. But what if alpha is equal to gamma? Now, in principle, you know you have a bounded sequence in W11, so what you can do is that you can find a subsequence that weakly converges to some u, but now this function u is a function of bounded variation, meaning that u is a L1 function and its distribution derivative can be identified with a Radon measure. Okay, so we were able to address both cases. They follow the same principle that I'm going just then to briefly describe it, but the techniques actually have to be quite more involved for this case. But we are lucky, it turned out that this function actually, that in principle could be any BV function, but no, in fact, we end up in W11. So we are able to prove that, after all, U is in W11, but this is a non-trivial, this was a non-trivial analysis. And then regarding compactness for M, so again, this is a non-negative term, so what we get, so we know that G of Mj is less or equal than a constant. So if you add an assumption on G, namely that it is coercive, meaning, for example, that the limit of J of t over t, this is equal to plus infinity as t goes to plus infinity, and then use the criteria of Lavallee-Poisson, and then you prove that this is equiintegral, Mj, and so up to a subsequence, or if you want Mjk, does converge to some M. And then it's easy to prove, because you have weak convergence, it is easy to prove that the pair UM, it is in, so in this case, UM, it is in this, for Q, it is our alpha over gamma, and for R, the regularity of M, it is 1. So we have our compactness. So then how the rest of the proof goes? Now, remember then we would have to prove lower, so we already have compactness, then we need lower semi-continuity with respect to this compactness that we have just shown. And this relies on I would say, non-obvious properties on the function f, namely it is convex. It is a convex in the pair. It is a convex function, we can prove it. It is convex, it is lower semi-continuous, so we have a typical result in the calculus of variations. So our functional J is in fact lower semi-continuous, and that was I was arguing in the beginning. So then we prove existence of solutions. So this pretty much ends my detour to the blackboard, and let me tell you what are the results. One that I've just shown you. So first result on existence. So alpha is greater than 1 and less or equal than gamma. These are the assumptions that were there before. We are assuming that G is coercive. This was to get compactness on M, and V is in L infinity. Then we prove that we have a solution to our variational problem. Okay? If we ask more for the function G, then we get a little bit more. Namely, if we ask G to be greater or equal than some power, say theta plus 1, where theta is a positive number, and we can ask a little bit more for V, then we can also prove that there exists solution now in this set. So what happens is that this coefficient now is greater than alpha over gamma. And the way you play this game is very similar, because what happens is that you go to this proof here, and then you get more for M. If you get more for M, you go back where we did the computations here, and then you play the game differently with these exponents. You choose the exponents, and you get higher regularity. And like I said, this is based on the convexity and the compactness and convexity of the functional J bar. And then we are also able to prove uniqueness. For the uniqueness, I mean, given any Q, any R greater or equal than 1, V, it is in this little backspace. Now, what we are asking more is that G to be strictly convex. Then, in this case, it may seem trivial, but then again, because this is just the dependence on M, then we have to play with the couple, the PM, and this still we can prove that at most there exists one solution. So if we go back to the previous results, if we add this assumption of G to be strictly convex, we have existence and uniqueness of solutions. Okay, just there is a case where we can explicitly compute, or at least have a closed form for the solutions of our variational problem, which is when P is equal to 0, we are able to prove that this U bar is identically equal to 0, and our function M is given by this. So the G star, it is just the Legrand transformation of G. This is the derivative computed at V, our potential minus H bar, and H bar is the unique number that satisfies for which the integral of M is equal to 1. And for example, in particular, if you take this function for capital G, then the Legrand transform is given by the squared of the positive part over 2, and we have these explicit formulas for our M bar. In particular, if this constraint is satisfied, if you remember, it was the first computation I was making on the blackboard, proving that there is no in general classical solutions. This is like a threshold. So if this condition holds, then M is given by this formula. Of course, points at which we have equality M is equal to 0. So this is no longer a classical solution. But if the inequality is strict, then we actually, I mean, by the uniqueness result that I've just shown you, this triplet is actually the unique classical solution for our original problem, our mean field game. And because we have this closed form for the solutions, they allow us to validate our numerical results. So let me show you in 1D. So let me start with 1D. So here I'm fixing P equal to 0, because it is the case that we have our solutions. This is our function, again, and for example, fix these parameters. And now what I'm highlighting here is that the V is the 1/2. So this means that our potential, the average is equal to 0, and it satisfies the strict inequality that I was mentioned before. So we do have classical solutions. So this is V, this is our M. Careful, because the values here on the Y, they are not the same. So and what we notice is that M, the graph of M resembles that of V. So, and what else? So I'm not plotting here the error, because numerically it is equal to 0, nor the value function U, because that is also equal to 0. Now, if we go to a borderline case, I'll say a threshold, which is this coefficient to be 1, which means that V is equal to is 0 at a point. So M V is equal to -1 at a certain point. So it means that M is equal to 0 at that point. Still, we have a nice M that resembles, so M resembles V. Then, if we go to a bad behaved situation, which is V violates that condition that ensures classical solutions, then what we see? Well, when V is not too negative, that's what it means here, then okay, M resembles more or less V. Otherwise, M is equal to 0. So this is penalizing. So when this is telling us that there are no agents when V is too negative. Okay, so it's penalizing the high density areas. And then we also try to understand, then we fixed V, the potential, the coupling, and alpha and gamma. And then we try to understand what happens if you vary P. P equal to 0, it's the case that I've just shown you, that we have the closed form solutions. And then what you see is that as P increases, the agents want to move more and more. It means that they spread around, so the graph is flattened. And so we go to a more homogeneous distribution of agents. And also, we studied the, sorry, what did I do? Oh, okay, sorry. This was just, I mean, here, before I didn't plot the value function u, because for p equal to 0 is identically equal to 0, and now here we just the plot of the value function u. And then, still in the one-dimensional case, we try to understand the impact of the congestion parameter. We tried different ones. So when what is happening here, what did I do? One slide too fast. So the regions, you see, so this is the case where the coefficient is such that V has areas where it is too negative. So and nearby those areas, so the bigger is alpha, the smaller is m. So it makes it so that the agents really don't want to be there. So the bigger alpha, the more congestion effects appear. Otherwise, when V is sufficiently big, then the big, sorry. Okay. The bigger m, the higher the density. So, and this is somehow expected because the mass is conserved. Okay, so we also did some numerical experiments for, so this is the value function. We also did some numerical experiments for the two-dimensional case. And here, again, it's where we validate our results. P is equal to 0. So P here determines preferred direction of motion, but here it is 0, 0. So this is our potential. This is m. So when V is not too negative, the graph of F resembles that of V, and the symmetries are respected. While if you now put a P that different from 0, 0, so this is your potential, quite symmetric, and then you see that the graph of M, well, still resembles that of V, but there is some asymmetry, and this is the effect of this preferred direction. Okay, things so this is the value function. Things that I would like to mention, well, drawbacks, well, this new variational principle that we proposed relies on the particular form of the Hamiltonian. It's a power-like Hamiltonian, but still it is very typical in the mean field games business. And of course, we would like to improve regularity of solutions, and we would like to stand to the time-dependent and second-order cases. Let me also tell you that I didn't tell you the whole story of this paper. So in particular, in the two-dimensional case, we were also able to study the remaining range of values for alpha, namely when alpha is between 0 and 1, because by a transformation, we are able to transform the corresponding system into one that satisfies exactly the requirements that we need in order to establish the existence of solutions. And we also studied other related mean field games for different Hamiltonians, and using some transformations, we were able to say some things about these cases, but I decided not to include them here. And if you want to see the details, you can, the paper, which was recently submitted, it is available in the archives. Thank you for your attention.
Further questions?